Yeah, Fairwinds. I think Brian was talking about Fairwinds a little bit. And that's who we are. That's why the slide says Fairwinds. And that's our mission statement. So in a nutshell, we have a team of expert Kubernetes people who've been working with Kubernetes for a long time, really understand it. It's our core competency. And we help our clients build and manage Kubernetes clusters that are secure, reliable, and efficient. We're pretty good at what we do. So put that out there and just introduce ourselves really quickly. I'm Stevie Caldwell. I'm the senior engineering tech lead here at Fairwinds. And I'm actually celebrating my 5-year anniversary at Fairwinds this month. So,
yep. And like I mentioned when Steve was out, also an SRE at Fairwinds, and off and on, I can't tell you how many years I've been here, but it's been longer than 5.
Oh, one-upping me, Brian? Nice, real nice. So anyway, yeah, we know that things are running behind. So we're going to do a sort of lightning talk version of what we were going to do today in an attempt to help get things on track with timing. So we're going to kick it off with Brian. So yeah, we're talking about mastering Kubernetes strategies for optimal performance and scalability. And we are optimizing our performance today by trying to go be quick and efficient in our delivery. So we're going to start off talking about the performance part of that. And Brian's going to start off with reliability.
Yeah, so for clarity, I mean, performance can be any number of things. Someone actually just put a comment for the previous talk that any of you integrated cost metrics and budgets as SLIs or SLOs into their systems. And so, it can go from how fast things are going, how well things are staying up, requests being handled and whatnot. And I do think that, especially for what we do on our team, reliability is a big part of that. Just a bit of disclaimer, my sections of our presentation are going to go a bit differently than planned. For better or for worse, I ran this presentation for and asked for feedback from my 5th grade daughter and one of her friends. And first, they made me add pictures to my slides. So you'll see my daughter's favorite anime character, Toga from My Hero Academia. And then her friend's quote unquote celebrity crush, Steven Sanchez. And then beyond, I have never even heard any of the songs.
No idea who that kid is.
Yeah.
Okay.
Anyway, that said, working with 10-year-olds ended up turning this into quasi fan fiction. So if you'll bear with me, let's go through a little story. So let's imagine that Steven Sanchez has just announced a tour, and his website is about to get slammed with a bunch of teenagers asking for pre-sale codes. And he realizes that not only are they going to be doing that, but there's a CVE on node images. It requires a node replacement to fix it. Being a pop star, of course, takes a lot of work. And so Steven's idea of downtime on the road is, you guessed it, optimizing uptime for Kubernetes clusters. That bad pun went way over the 10-year-old's head, unfortunately. So the first thing he thought about was making sure that his pods have pod disruption budgets here. Those are there for voluntary disruptions, like replacing nodes in a cluster intentionally, things like auto scaling going up and down, or for cluster upgrades and whatnot. So it's really important you set these so that you have enough replicas to keep up with demand. However, there's also the corollary to this is you need to make sure these are set correctly. Otherwise, if you don't, sometimes pods can't be evicted when you want them to. And you have to kind of dig around to figure that out. So that's and for clarity, these are all kind of situations that we faced before, which is one reason I want to include them here. So let's say the PDVs were there, the node roll went smoothly. Steven Sanchez now sees that some of his pods are crashing because they don't have enough memory. And all the pods on one of the nodes are starting to have errors because one of them didn't have limits set. And it's causing the node itself to start crashing. So using his favorite open source resource validation recommendation tools, Polaris and Goldilocks from Fairwinds, Steven set his pods up with resources, and the crashes stop. Again, at this point, both kids' eyes were totally glazed over. But again, a lot of these are things we all know about, but I think it's worth keeping them in mind as part of what helps with reliability in a Kubernetes cluster. Let's say all of a sudden, all the traffic starts coming in, and Steven notices there's some latency building up between 2 different services that are used to track and send out those presale codes. Knowing that these pods might be spread over different nodes or potentially even regions, he adds pod affinity configurations to those workloads so that they can be scheduled on the same nodes and potentially reduce that network latency between them. However, potentially during this time period, there could be an alert that one of the availability zones that the cluster's in goes down. And Steven, who in real life actually is a partner with Lenovo of all things, has to get to a meeting. So he quickly throws some topology spread constraints onto his deployments that the replicas will be spread throughout all availability zones. And so if this one availability zone goes down, he'll make sure that there's still plenty of pods elsewhere to handle traffic. And with the crisis over, Steven heads out to his meeting, gets lots of tickets sold, and my kid's feedback was that's very intriguing. And with that, I'll hand it back to Steven.
That was a delightful story. I like the way that you did that. I'm going to do something. My next part is going to be a little less intriguing and captivating. I don't have any narrative for it, but I'm going to talk about, spooky seasons. I'm going to talk about something that's spooky, and that's DNS. DNS is very scary stuff. DNS is also one of those things that we tend to overlook because it just works usually. You deploy a cluster, core DNS usually is what's deployed for you for DNS service discovery, and it just works like magic. I'm sure all the people who work on it would not tell you it's magic, but for us, for our purposes, it looks like magic. And so that means that when things start to go wrong in your cluster, your ticket sales are going on, or you just have a lot of an increase of traffic to your cluster, you can start to have some performance issues, and DNS issues don't always, they're not always straightforward host not found issues. It can manifest as general slowness or application latency until you finally discover that it was DNS. Like we have, so we have, a Slack bot that puts out this haiku because we've encountered DNS coming up to, bite us often enough that we've decided, that it's worth being able to trigger that. So we're going to talk about, 3 key optimizations that can enhance DNS efficiency and reduce latency and improve the reliability of service communications within your Kubernetes cluster. So the first thing we're going to talk about is dots. I think everyone has probably heard about dots because dots is a very popular go-to when it comes to trying to optimize DNS. And in order to discuss dots properly, we're going to start off looking at a resolve.conf file, right? So resolve.conf, that's the file that exists in every container, influences the DNS search process for that container. So by default, if you do nothing else, your resolve.conf will look something like this. There'll be a name server, which has an IP address, and that is typically the cluster IP of your cluster DNS service, so core DNS. And then we have the search and this local search domains and the in-dots option. And these two together determine how DNS will try to resolve a query if the query is not for a fully qualified domain name or a host name that ends in the cluster domain, like cluster.local. So neither of those things is the case, and the host name that you're querying for has fewer dots than what's specified by the in-dots parameter, which is 5 by default. Core DNS will go through this list, appending each search domain to the queried host name until it either receives an answer or it has to forward it upstream to its own name server. And this is helpful for service discovery, as you can simply refer to a service by its name, and you'll get the correct service pretty quickly iterating through this list. The trade-off is when you have services that query external domains, and those are never going to resolve internally, yet you still have the search path expansion to go through before the request gets forwarded to a name server that can actually give you an answer. Additionally, each query is actually 2 queries in parallel. There's an IPv4 query and an IPv6 query. So you potentially have 8 queries being sent to core DNS for a single host. And if you have a number of services to communicate with external services, DNS lookups can get expensive and have a trickle-down effect on even the in-cluster resolution latency, right? So this becomes like not super obvious when you're looking at performance, but it's a thing that tends to add up. So, how do you mitigate that? Dots, like I said. So a couple of things that you can manipulate in this file in various ways, or not necessarily in this file, but so the first thing is the definition of the fully qualified domain name. So for our purposes, right, we consider a fully qualified domain name often just like www.example.com. And in DNS, the fully qualified domain name is actually indicated by a trailing dot at the end of the host name. You can test this out yourself by running Wireshark on your local machine and running a container with TCP dump inside your cluster, and send the TCP dump, pipe that through to your Wireshark, and you can watch it like in action. I did this with example.com and witnessed when I queried, did a dig for or curled for www.example.com, I got a total of 8 lookups before I got the answer I needed. And when I queried for www.example.com it went straight to the upstream name server. So that expedited that process of looking for an external host name. The other thing you can do, so you can add that. So if you in your application, if you specify an external service that you need to talk to a lot, you can just add a dot right to the host name, and that will solve that problem for you. It does require you hard coding it and that kind of thing, but it is a option. The other thing you can do is set DNS config in your pod spec. DNS config looks a lot like this. There are a number of options you can put in here. This is the kind of thing you do want to be careful about, because changing things in here, you could adversely affect traffic as well, right? None of this is like, oh, if I throw this in here, it's going to completely work and be perfect. You obviously want to be careful about the changes that you make, how many dots, like using in dots. If you put, I think too few, then you could wind up having issues with service discovery within your cluster, right? But with something like in.3, for example, if your services are referring to each other by their singular service name, that will still go through the search expansion list in core DNS, but also then www.example.com in the situation where you have in.2 would automatically be forwarded out and make that a little bit faster. The next thing that you can tweak is core DNS itself. Is often installed and left alone with its defaults, but tweaks can be done to it to help it to be more performant in high traffic clusters. Most important thing before you make any changes to core DNS, though, is to have some data, right? And so the first thing I would say is that you need to monitor core DNS, monitor the key metrics. Core DNS exposes some really good metrics like cache hits, latency, and of course you have resource utilization that's exposed through standard metric server stuff. Core DNS has a Prometheus plugin that you can enable pretty easily. And then you have this information that you can use to do things like set proper resource allocation, like Brian had mentioned before, for your core DNS pods to make sure that they don't run out of CPU or memory. Core DNS tends to be CPU bound, so that's a good metric to track on and to keep an eye on. You can use the cache hits information to tweak the cache size and the TTL for cached objects. And then the last thing is how you scale core DNS, right? And we're going to talk about scaling later in this presentation, but here, core DNS actually has the Helm chart lets you either choose to use the core DNS autoscaler, which is a proportional autoscaler, or to configure your own horizontal pod autoscaler. And people have different ideas on this. I think because core DNS tends to be CPU bound, the CPU based HPA is actually a fair game for using for core DNS. You can also use other internal metrics like how long it takes for the health checks to process, because that can be a measure of how well core DNS is able to process your requests. And this will vary by environment, but that's a thing to put into place to sort of keep an eye on core DNS itself. And then the last bit is node local DNS. And node local DNS there's not a whole lot to say about it. Like you pretty much install it. It's essentially deploying core DNS in caching mode as a daemon set. DNS queries are intercepted locally, like node local pods use host networking, and they alter the IP tables rules a little bit so that queries from pods going to the cluster DNS service are actually intercepted by the local DNS cache. And then, if it finds the entry in the cache, you get your answer there. Otherwise, it forwards it upstream to the actual core DNS pods. And that takes the load off core DNS pods by reducing the number of queries that are sent there, and also reduces the latency of lookups by decreasing the frequency of pods having to reach out to other nodes to get their queries resolved. So that is my part. And then Brian's going to talk about cross-zone load balancing.
Yeah, and before I do that, I just want to address one of the comments asking about how to get a good handle on managing all the strategies from the reliability section. And not sure if I'm, and potentially in those kind of live situations, that becomes a little tricky to add that in. I think a lot of this you'd want to have configured beforehand before a situation shows up. And for what we're doing, which is oftentimes managing add-ons at a cluster, say ingress things, monitoring, auto scaling, gateways, all of that. We do have a lot of kind of templates for how we set up those Helm charts and such. And so that's really important. The other is how you might use things like policy or configuration checks to make sure that workloads do have certain parameters set, like make sure there are PDBs as part of a Helm chart potentially, or that affinity or topology is included on that, or the resources are set. And with different checks for there's all sorts of ways you could check, either at an admission control level for workloads coming to the cluster, all the way back to Git and CI, so that as developers are working on things, they can make sure that those configurations are there, well before anything ever gets deployed to a cluster. Cool. I will take it from here. This is an interesting one that kind of came up recently with an issue with the client, so I thought it'd be fun to bring that in. And after doing one on Steven Sanchez, of course, for my daughter's sake, I had to do a little story about My Hero Academia. So, and this is actually happening after 10 years of epic excitement and rabid fandom, the final My Hero Academia episode is actually about to drop this Saturday. And Crunchyroll is a streaming service that shows the show in the US. And I can only imagine that right now their engineers are hard at work making sure their clusters can handle all the traffic that's going to hit their workloads. So assume they're maybe using AWS network load balancers with a standard setup. And you can see that on the left-hand side of that picture. You have a network load balancer, and from that, you have a load balancer node in each availability zone. And for every request that comes into the NLB, one of the standard configurations people use is to have a round-robin algorithm that routes requests evenly among the load balancer nodes. And then each of those load balancer nodes routes requests evenly among the healthy targets in each of its respective availability zones. Now, that can cause a problem because pods aren't always spaced out evenly in different availability zones. So say if you have a total of 10 pods, 2 are in one zone, 8 are in the other, they're going to get very disproportionate amounts of traffic. So in the one zone with only 2 pods, while each zone is getting 50% of the traffic, those 2 pods are getting 25% of the traffic, and then the remaining 8 pods are getting just over 6% of the traffic. So that can both overload some pods, but when it comes to figuring out what resources to set for pods, that's going to be hard, because if you want to look at past performance and past usage, it might be wildly different depending on where a pod was located. And so by using cross-zone load balancing, that lets load balancer nodes route traffic to all healthy targets in all availability zones. What that means is that, so for whichever load balancer node, it's going to know about all healthy targets in all availability zones and be able to, and will route traffic evenly among them. And that includes, both of these here. And that's illustrated on the picture on the right. This evens out traffic and also, again, allows folks to make informed decisions about setting resources. A couple things to note here. One of the things we found here, one of the reasons we started using this and discovered this, is that when I said route traffic to healthy targets, that's what it's supposed to do, only route traffic to healthy targets in availability zone. And while the documentation doesn't say that this is the case, what we found was that if all of the targets in a specific availability zone are down, that node may then send traffic to all of those targets, despite the fact that they're all unhealthy. It's a little quirk that's there. And I apologize for any My Hero Academia fans. Quirk is also a superhero skill in that world. So just to understand, that's not what I meant by this. So yeah, that is actually why we did turn this on for a client, so that we wouldn't have that issue. And but there can be some great performance benefits out of this. Now, another thing to keep in mind is that I don't believe there's cost for network traffic within availability zones, but there is cost for cross-zone networking traffic. So you may see a little bit of an increase in that as on your AWS bill, and it could potentially increase latency a bit if you have, requests being fed to through different availability zones. So especially with the latency side of things, you're going to have to see, is that latency more important than pod load? And either way, if you use topology spread constraints and make sure that pods are spread across different nodes or different nodes in a consistent way, this may not be an issue at all as far as needing this system. Lastly, this is, I think, mainly turned on by default with application load balancers, but with NLBs, gateway load balancers, and the classic ELBs, this is something that you have to configure. And someone asked about that, and yes, as far as I can tell, at this point, the cross-zone load balancer is specific to AWS. I did poke around elsewhere and didn't see that. It's not that it's not necessarily there, but that the specific feature seems specific to AWS. And yeah, that's it on AWS cross-zone load balancing.
All right. So the next thing we're going to talk about is storage. Storage is also another overlooked opportunity to get better performance out of a busy cluster, especially specifically persistent storage. So it's all about storage classes, really, and I'm going to kind of whip through these. So things to consider to optimize how you use persistent storage is, first of all, to use dynamic provisioning via storage classes. Creating storage classes means that you're not wasting resources. You're not, deploying, creating, or reserving, I should say, volumes under the hood that aren't being used yet. Just in case the volumes get provisioned at the time that they're needed. Also, it decreases human error from having to manually create persistent volumes and removes the need for an administrator to provision. It's one less thing that you have to do, right? And one less bottleneck in the deployment process. The next thing to consider is creating the storage classes that you need. So a default storage class is often installed by your managed Kubernetes provider or the CSI driver itself. Will often install a storage class and set it as the default. And it might not be suitable for your needs, right? This is the storage class that workloads will get if they don't specify one. And if you don't specify a good, solid storage class that's suitable for the most common use for your organization, you can have a lot of performance issues just from that alone, from using types of storage that just aren't appropriate for the workloads you're running, or you could run into cost issues because you're maybe overdue. Like maybe the default is using something that most of your workloads don't need, right? Like you don't need a GP2 necessarily if you're just saving logs or something like that. It's also great to create additional storage classes aside from the default one. So those can be customized to meet specific workload requirements like cost and performance. And that will also improve the efficiency of your stateful workloads. And then one of the biggest headaches with persistent volumes is that sometimes your storage backend that you choose is topology constrained. For example, EBS volumes, have to be in the same zone as the pod that's bounding them. And so making sure that you're using the right volume binding mode in your storage class is important. Sometimes the default is immediate, which means that as soon as a persistent volume claim is submitted to the cluster, a persistent volume is instantiated and bound to that claim, which could cause issues if the pod that's going to mount that volume hasn't been scheduled yet. And there are some things that the scheduler can do. Persistent volumes are labeled with a zone label, and the scheduler tries to take that into consideration when scheduling a pod that it sees as mounting persistent volume. But it's best to even not leave that up to chance, because we've all seen pods that just won't come up because they can't mount a volume, right? So if you set the volume binding mode to wait for first consumer, then the persistent volume isn't created until the pod that's going to mount it has been scheduled to a node. Immediate volume binding mode is great for volumes that don't have a locality constraint like EFS, but for things like EBS or what have you, wait for first consumer is a good mode to use. And the last bit is in terms of managing storage, enabling volume expansion. So that allows the storage to be grown to Kubernetes to grow the storage, increase it as needed. Disk latency can increase as a disk fills up. So it's a great idea to keep an eye on that. And then, you can even set up some automated way of monitoring that and then automatically patching like your manifest to increase the size of your disk before it gets out of hand, right? And then lastly, volume snapshots in that same category enables you to capture your persistent volume state at a specific time, so that you have some data protection and disaster recovery. So that's it for storage. And now we're going to talk really quickly about scaling. And I think the first slide is mine as well. Yeah. So in regards to scaling, we talk about scaling a lot, super important. I think they talked about it, also in the platform session that was before ours. So scaling can be either horizontal or vertical, right? So horizontal scaling means you create more copies of the thing. Vertical means that you're increasing the resources of the thing, of the workload. Stop calling it the thing. So horizontal pod autoscaler is something that probably everyone is familiar with. It's already enabled in the API server. It's easy to configure. The limitation is that it is really best for scaling based on the most basic of metrics, CPU and memory. And if you want to enable other scaling metrics using the custom metrics API or the external metrics API endpoint, that's possible to do with the use of an adapter that will bridge the source of the metrics that you want to pull in with the API server. But it gets a little complicated, and it's not super neat, and it feels kludgy, quite frankly, right? And you can only have one of these per endpoint. So you can't, for example, have a Datadog source and some sort of, other source that are going to use the same external metrics endpoint. So you sort of have to choose. So that's, and that's one of the limitations of it. And also some people want to scale their workloads to 0 if they don't have, a lot of traffic, if they don't have any traffic, right? And HPAs don't allow you to scale to 0. So the next step up would be something like Keta, which is an event-driven autoscaler. And Keta is cool because it allows you to scale off of any resource that implements the scale sub-resource in the API. And it also allows you to use almost anything as a source for metrics. It creates you create a scaled object, which is a CRD that Keta installs. And in that scaled object, you define a trigger, which Keta has a bunch of for various external sources. You can also create your own trigger, I believe. And then you specify the source that you want the trigger to come from, the metric, the threshold, all that stuff. And Keta actually creates an HPA object under the hood for you. And then, we'll scale on those metrics. And Keta can also scale to 0, which is, like I said, useful for some people. And then, so those are both different types of horizontal scaling. And the last type of scaling here, I call it right sizing. It's really vertical, like vertical scaling, right? So increasing the resources for your pod. And there are a couple of options out there. Many of these solutions offer both a recommendation engine, so essentially provides you with data to adjust your workloads on your own. And some of them have features that allow you to apply the recommendations automatically. So we mentioned, or Brian mentioned Goldilocks. That is a Fairwinds open source project that we've had for quite a while, and is one of our like most popular projects. It uses the vertical pod autoscaler VPAs under the hood, actually, and it can be by default it uses auto mode in VPA, so it shows you recommendations. It uses metrics taken from the metric server, or you can use Prometheus, and observes the performance of the workload over time, and then gives you a recommendation on resource requests and limits to set based on whether you want burstable QoS or guaranteed QoS, right? And you can also turn it on to use the actual update mode in VPA, but that's not the default. A couple of other things that we've heard of and been looking at recently, but don't have a lot of experience with yet, but just wanted to throw out there, StormForge. StormForge uses machine learning to make recommendations based on optimization parameters that you set. And it also has the ability to apply those changes, those recommendations automatically. And NetApp has something called Cloud Insights, which also does recommendations. I'm not sure that it has automated right sizing yet, but it does do recommendations. And some combination of those things will definitely help your workloads to scale and handle increases and decreases in traffic. I will mention that if you wanted to use VPA and horizontal scaling at the same time, pretty much Keta and then some VPA solution is the way to go, because with HPA, because of the limited metrics that you can scale on, they clash and it can get messy. All right, and then Brian.
Yeah, so from pod scaling, let's jump up to the node side of things. And I think most people are using Kubernetes or aware of basic cluster autoscalers, which open source tool, core part of Kubernetes, also comes built in on a lot of the cloud providers' managed systems. That has had some limitations in the past, and so I want to talk about the node auto provisioning systems that we've been seeing come out over the last couple of years. And as far as story time goes, I wasn't quite sure what to do, and then my kid gave the obvious idea of doing an epic crossover between the two things. So let's actually pretend that we're having an epic crossover between Steven Sanchez and My Hero Academia, complete with comics, TV episodes, Fortnite characters, and extremely profitable merchandise. Let's also assume that the traffic for this undertaking will be at its peak before and after school and on weekends. And the engineer site, the crossover site's engineers want to make sure they can be as efficient as possible, as quickly as possible, and also be able to meet demand at the right times. So before, when they were building clusters, you'd use traditional node groups with like a single node type, say like an M5, 4A or whatnot. And cluster autos, you would set minimum and maximum for those, potentially have different node groups, say if certain pods had more intensive memory requirements or whatnot, and using things like taints and tolerations and node selectors and all that, you would make sure that pods got on the right node groups nodes, and cluster autoscaler would handle making sure that if nodes need to be pods need to be scheduled on nodes and there wasn't capacity for them, new nodes would come up, and if the cluster was underutilized, it would go down. But again, you're always in these blocks of what specific, like a node with 8 CPUs and 16 gigs of memory or whatnot, and couldn't really be flexible beyond that. So let's say that Steven Sanchez, who is on top of all things pop culture and Kubernetes, suggests trying out node auto provisioning tools. And with that, there's a lot of different tools out there, but by and large, most of them allow you to say set a maximum and maximum amounts of, say, CPU and memory you want to use for your workloads. And then the provisioner will figure out the right combination of nodes for those. And you can specify all sorts of different node types, say an entire class, like just use M5 nodes or whatnot, or just let the provisioner do it, have at it with whatever's available. Furthermore, a lot of these let you use spot nodes as well. And some of them allow you to have some different features alongside of that are related to, both cost and when things are scheduled. So first, our little team looked at Carpenter, which is originally built by AWS, but it's not part of the CNCF SIG auto-scaling group. It has providers, last I checked, in AWS, Azure, and Alibaba Cloud. It's open source, so while you do have to manage it yourself, it does have a lot of flexibility and a lot of configuration options and a lot of extensibility too. And one thing I really like about this is that, and I haven't quite seen this in some of the ones that are tied to specific clouds, is that you can set node pools that you make to use both spot and on-demand instances, meaning if spot instances are not available, though while preferred, Carpenter will spin up on-demand instances for those node pools. Now that said, most of these tools will have some kind of loop that they go through, say, over a certain period of time, they'll look at the current makeup of nodes in the cluster and make them more efficient. Say, okay, we can, just like a cluster autoscaler would, but again, with a lot more complexity. So that's Carpenter there. A couple of the cloud providers, specifically Google and Azure, have managed node auto provisioning. So you can get that in GKE and AKS. I think it's still on beta in AKS. It just came out pretty recently. And so because they're managed by cloud providers, they generally don't have all the features that something like Carpenter might have. But engineers really only have to think about configuring node pools instead of making sure the provisioners are configured and running as well. So that, if you're on one of those clouds, it may be worth investigating if you're interested in this. And lastly, there's third-party tools. Spot.io is one we have experience with, and while it's a paid service, it can have a lot of other features like things around efficiency and cost optimization, let you know, how much your resources are costing you, and potentially help you figure out what might be a better makeup of what nodes to use or how to configure them. Some of them also have some cool features, like Spot has shutdown hours, which will essentially remove node groups during certain hours that are specified. So for example, during the school hours when the kids are obviously not on their phones looking for these things. And the last thing with something like Spot is that it's available all over the place. So like EKS, GKE, AKS, you can also use it on COPS, you can use it on OpenShift, you can even use it on ECS. So it's great if you have a pretty wide kind of footprint in different places, but want a consistent tool to help manage all of that. All right, and that's the end of that. I will turn it back to Stevie to do a very quick overview of us.
Has to be super quick because we are over time.
We are a company that does stuff. This is our shared responsibility model. It's probably very familiar if you've seen AWS's, and it just sort of outlines where we come in, where the customer has responsibility, and the kind of things that overlap. DNS, like we were talking about, monitoring. Those are things that we work on together because there's no really big line there, but Fairwinds takes care of the cluster networking, the control plane and worker nodes, manage Kate's add-ons, and things like that. And we partner with you to make you as successful as possible. And that, I believe, is the end.
Wow. Thank you. And if you, both Brian and Stevie were answering questions as the other one was presenting. So if you have more questions, please feel free to drop it in there. Thank you, Brian. Thank you, Stevie. It was great to have you here.
Thank you so much. Great to see you again.
Bye.